Hello. Today we're going to conclude the Jerusalem Astronomy Contest lectures with Chapter 27 and Chapter 28. So you recall last time we talked a little bit about the end of the universe, and this time we're going to look at cosmology from another point of view. We're going to try to extend it back to the beginning of time. We've already seen that approximately 27% of the mass of the universe consists of normal and dark matter, and the remaining 73% is basically due to this mysterious energy force, this energy that we call dark energy. So dark energy right now is dominant in the universe, but it wasn't always dominant. So prior to about approximately 4 billion years ago, the universe was matter dominated, and dark energy was relatively unimportant at that point in time. The radiation density today, that's the microwave background that we've already talked about, if we convert that energy into its mass equivalent, the density would be 5 times 10 to the minus 31 kilograms per cubic meter. But there must have been a time in the past when this mass and that is the mass equivalent of radiation and the mass equivalent of energy were equal. And at about roughly some 50,000 years after the Big Bang, the size of the universe was about 1/6000th, 1 over 6,000 of what it is today. And the temperature was something on the order of 16,000 kelvins, which meant that the universe was actually emitting in the near UV region of the electromagnetic spectrum. So beyond this point in time, matter actually dominated. Particle production occurred for electrons at somewhere around a temperature of about probably on the order of 6 billion kelvins. But protons, the temperature was even higher. So protons actually appeared on the scene after the Big Bang at an even shorter period of time. And that was when the temperature of the universe was at about 10 trillion or some tens of trillions of degrees. So at about 10 billion degrees, at a much cooler temperature, about 3 orders of magnitude cooler, most photons at that point in time had the energy had cooled down enough that we could actually get something that we've talked about many weeks ago, which is pair production. And well, I guess we didn't really talk about pair production, but what we did talk about actually was the fact that when an electron, for instance, and a positron react with one another, that is, they collide with one another, they annihilate one another. So here's two pieces of matter that actually undergo annihilation. And what we did see was that when that happens, when these things annihilate, they're going to produce gamma photons. And those gamma photons are actually going to go off in a direction that is actually perpendicular to the direction that the electron. Well, if you have the point is, if you have a sufficiently energetic source of gamma radiation, then in fact, what can happen is the reverse of this. So when the question comes about how can you get something from nothing, that is, how can you get matter from energy, in fact, if you have a gamma photon heading this way and another gamma photon heading that way, and they collide, it's also possible to produce an electron and a positron. And if we were to actually show this kind of thing, this kind of reaction, where we've got a gamma plus a gamma, you notice that this is massless, and it doesn't do anything to an atomic mass or to an atomic number, but this is going to create two particles, one of them an electron, and the other one a positron. And we still have conservation both of charge, because these charges are going to annihilate one another, and also what's going to contribute to the atomic number is also going to sum to zero. So that equation would actually balance. So we call that pair production. And pair production, that is the formation of a particle and an antiparticle from two photons, is a possibility, and particularly this happens at temperatures somewhere around, as I said before, about 10 billion degrees, because at that temperature most photons have sufficient energy that pair production can actually take place. But once the temperature is approximately 1 billion degrees, gamma photons no longer have enough energy for that to happen, and then the electron-positron pairs are going to annihilate one another and reform gamma photons again. In about the first 100 seconds after the Big Bang occurred, all the fundamental particles that we have in the universe are estimated to have formed. Protons and neutrons froze out when the temperature dropped below approximately 10 trillion degrees. And at that point, the universe was 10 to the minus fourth, that's 1/10,000th of a second old. Electrons froze out later at a temperature of approximately 1 billion kelvins. So if we actually look, and there is somewhere in your book, and there is a chart which is much better than anything that I could draw for you. It's on page 687, talking about the evolution of the universe. So what I want to call to your attention, this is figure 27.4, and what I'd like to call to your attention is the fact that in this figure, you've got a couple, it's a little hard to read everything that's going on here, but the universe is basically divided up into time periods, which we'll refer to as epochs. And there's one epoch here that takes place, basically, it's from a period of time that's about 10 to the minus 43 seconds up to about 10 to the minus 34 seconds. And that particular period is labeled here, well, there's something labeled as the Planck, named after Max Planck, the Planck epoch. And that is apparently anything that takes place prior to 10 to the minus 43 seconds. So at that extraordinarily brief period of time, this is the point of time from the zero time of creation up until the instant that the Big Bang actually occurred, where we have a universe that's basically infinitesimal and infinitely dense. And then this expansion takes place. So one of the things that you can get from this is the idea of just how fast and how large the universe becomes in a very, very short period of time. We don't really understand, we don't have physics, we don't have, perhaps when we actually have a good theory of quantum gravity, we might be able to get some kind of an understanding of what actually took place during this Planck epoch. But after that, it's abbreviated as GUT. These are grand unified theories, not one theory, but a series of theories that actually have to do with the unification of the four fundamental forces in the universe. So at this particular point in time, just like we say Hashem is one, all the forces in the universe apparently were one. It was a single force. And I think this ends, this period ends at about 10 to the minus 34 seconds. Starts at about 10 to the minus 43, goes to about 10 to the minus 34. I don't have the numbers right in front of me, but I think that's roughly the period. It's something approximating that. And then after that, we go into what is called a quark epoch. So what's happening is we're at extraordinarily high temperatures during the beginning of the GUT epoch, and even by the end, we're still in temperatures that are in the 10 to the upper 20-something power, or maybe even above 10 to the 30th power of kelvins. And then the temperature is now beginning to fall off, and during this quark epoch, this is the point in time when we start to see the particles that make up hadrons actually appearing. So the heavier particles, they actually settle out first, the hadronic subparticles, which we call quarks. And there are a series of quarks, actually 12 quarks, the particle type. So we've got a total of 12 particles: up and anti-up, down and anti-down, charm and anti-charm, strange, anti-strange, top, anti-top, and bottom, anti-bottom. We also have, as the universe starts to cool even further, then we start to see some other particles actually coming out of this. We start to see these lighter particles, known as leptons, freezing out of the mixture. So we'll see that during the quark period, the universe is transparent to neutrinos. So neutrinos are shooting out all over the place. Temperature's about 3 billion degrees, and this is actually sometime around, it's probably something on the order of when the temperature cools down to about 1 billion degrees, then we stop seeing pair production occurring, and that's when we get into this leptonic epoch. And this is going to occur sometime, maybe up into the first second or so of after creation. We're going to have, or maybe a tenth of a second or so, up to about a second or a few seconds into creation, where leptons are going to start to appear. So the leptonic particles are the electron, tau particle, and the muon. So we've got these three. And then we also have three even smaller particles that are associated with these. And each one of these is a neutrino. So we've got an electron neutrino, we've got a tau neutrino, and we also have a muon neutrino. And so these are, again, 1, 2, 3, 4, 5, 6, plus we have the corresponding antiparticles. So if this was the electron, then we're going to have the anti-electron, which we, as I said before, is the positron. So this, if this is minus 1, 0, that's 1, 0. And then we have the anti-tau and the anti-muon and the anti-electron neutrino, the anti-tau neutrino, and the anti-muon neutrino. So we've got a total of actually 24 particles here, 12 hadrons, or I should say 6 hadrons, and their corresponding antiparticles, and 6 leptons, and their corresponding antiparticles. And any time a particle and its antiparticle actually meet one another, they're going to annihilate. So anyway, that kind of shows us, again, looking at this table that's in here, figure 27.4, these various epochs, we can see that as the universe starts to get cooler and cooler, at the end of the leptonic period, what happens is we go into a nuclear period. So at this point, this is where primordial nucleosynthesis occurs. That's when do we actually see these particles agglomerating, coming together in some way, that elements, the elements of the universe are actually going to form. And this takes place, very early on, but it's into the second or multiple second range, maybe 100 seconds or something like that, where the universe is finally cooled enough that we can start to see this kind of thing, and nuclei begin to form. But the universe has to cool even more, considerably more, before it gets cool enough that we stop ionizing everything that we form and we actually get atoms. So in what is called the matter era, because we have, up until that time, we were in the radiation era. And as we saw early on, radiation dominated the universe. Matter was very unimportant. But now we're in the matter era, where matter is going to overtake radiation. Well, actually, this is occurring in the well, we're now into the billions of seconds. On the year scale, which is below that, it's probably in the 100,000 year range or so after creation took place. And then that matter era actually continues on. Galaxies atoms are forming initially. Quasars are forming. Galaxies are forming. We have towards the end of this, we have the peak era of star formation, and then we're actually at that point we're actually getting in. We're going from the nuclear, atomic, galactic, and then finally into what's called the stellar epoch, and that takes us really out to where we are right now. But now we're going out into well, at this point we're already in the billions of year range. Once we switch over from the matter era to the next era, which is actually the dark energy era. So somewhere out in the billion year range is when dark energy starts to overtake matter as the dominant density contributor in the universe. Okay, so 2 minutes after the Big Bang occurs, the universe is actually cooled enough so the deuterium can form, and this is the temperature of the universe now is in the somewhere around 900 million kelvins. So it's now cool enough that we can actually get deuterium. And you'll remember that we had deuterium forming in the sun, but it was different. The deuterium, the mechanism for deuterium formation in the sun was much different than the mechanism that occurred during the early part of the universe. So, for instance, and just to review something that we had back a number of chapters ago, that's basically what's happening in the sun. But in the early part of nucleosynthesis, before stars were formed, and when temperatures were very much higher, what was happening was something considerably different. We already had a whole bunch of primordial particles, so we had not just hydrogen, not just protons floating around, but we also had neutrons. And so, just like you have this reaction here, in nucleosynthesis, you'd have the proton plus a neutron. So that's the beginning of nucleosynthesis. And if we actually, at the end of nucleosynthesis, the temperature is down to 300 million kelvins, and at that particular point, there's going to be, if we actually, if I did this very, very carefully and we added everything up, we'd find out that we'd make one helium nucleus for every for every helium nucleus we had, there would be 12 free protons. So what we can do with that information, knowing that there's one helium nucleus for 12 protons, we can say at that point in time, once this reaction is repeated over and over and over again, what we expect is that 25% of the mass of the universe is going to be helium, and 75%, the remaining 75% will be hydrogen. And during the process of nucleosynthesis, probably very small amounts of things like lithium were also created, but these were extraordinarily tiny compared to the amounts of hydrogen and helium we had. So essentially we can say that those are relatively negligible. So a billion years later, when stellar nucleosynthesis actually begins to occur, more helium is going to be formed, and therefore, if we look, for instance, at the sun, we don't find that the sun is 25% helium, it's 28% helium. So during a period of time when the primordial nucleosynthesis has long ceased, and now we're into stellar nucleosynthesis, then at a much slower rate, we can start to build up a little bit more helium. But at the same time, at that point in time, when radiation was dominant, the ratio of radiation to matter was still, at that point in time, was still 5,000 to 1. So again, matter, even though I'm telling you that 75% of the universe is hydrogen and 25% is helium, that's really not, that's only true of the matter. But matter is only 1/5000th of, if we look at the mass equivalent of the energy, it's really only 1/5000th. So matter is relatively unimportant at this time. Since deuterium is not produced to any significant extent in stars, we know this now, that all the deuterium that we see today must have been of primordial origin. Okay, after a few tens of thousands of years, radiation actually starts to decouple from matter, and this is in what is sometimes referred to as the recombination period. Although technically it should actually be called the combination period rather than recombination, because it's not that anything was ever combined before. But what happens now is combination actually starts to occur. Now electrons and nuclei can actually combine, and the universe becomes nearly transparent to radiation. Prior to that time, it was opaque. What that meant was that radiation was going to react with something. It wasn't going to actually go very, very far. So microwave photons that we see today, that is the background microwave energy that we see, have actually been traveling through the universe since decoupling occurred about 400,000 years after creation began, when the universe was only 1,100th the size of its present size. So if we actually go back and we look at that universe, that would correspond to a photosphere around the Earth of about 14,000 megaparsecs, which is 46 billion light years. And we've spoken before about how you can have something that's further than light could possibly have traveled since the universe began, because that has to do with the expansion of the universe. The temperature was about 3,000 kelvins. And and the other thing that's really interesting, which I don't know whether I did mention this or not, but it's a point that is made in the book, is that from the time when we can actually, we have some idea of what was actually taking place from that 10 to the minus 43 second earliest time that we're actually able to figure out what was going on. At that time, the universe was something on the order of 10 to the minus 26 or so meters in size. So something extraordinarily tiny, much smaller than a quark or any subatomic particle, much smaller than a neutrino in size. When the universe was compacted to that point in size, during that period of time from 10 to the minus 30, 10 to the minus 43 to 10 to the minus 34 seconds, the period of time which we refer to as inflation, and you don't see that on the diagram on page, let me see, where do we have that? Where do we show inflation? Inflation, you'd actually have to go all the way to page 695, and you can see at this point in time, somewhere around the beginning of 10 to the minus 43 seconds, and I think I was using 10 to the minus 34. It looks like in here, if I'm reading this correctly, it's actually 10 to the minus 35. 10 to the minus 35th seconds. You can see the universe initially is not expanding during that first instant, and then all of a sudden there's a tremendous increase in the universe, and then it starts to level off again. So we've got kind of a plateau, a big period in here from 10 to the minus 43 to 10 to the minus 35 seconds. During this period of time, there's extraordinary inflation in which the universe is growing from about 10 to the minus 26th meters up to about 10 to the 24th meters. 50 orders of magnitude. So the universe has now expanded from something in that instant, has expanded from something that was the size of, something that was that was infinitesimally small, up to the size of actually the current size of our solar system. So that's how incredible the expansion was. And then after that, as I said before, it starts to fall off quite a bit. So we've got the inflationary universe. And before we had we understood this, it caused two problems for earlier astronomers. Or if the universe wasn't inflating like this, it really would have caused two tremendous problems. One of them is described as the horizon problem, and the other one is called the flatness problem. And so this is the question that's actually posed. Why should 2 points in this universe, where we said it was 2 point, where if we looked at that photosphere, so if we've got from our vantage point of the Earth, and we're looking out through this photosphere, and we know that radiation from the Big Bang has now moved out, and we're here, and we've got this huge photosphere around us, and the radius of this is 14,000 megaparsecs. So we've got a point up here, we'll call it point A, and another point over here, expanded in the opposite direction, point B. And if this is 14,000 megaparsecs, the diameter, or rather the radius of the sphere, why should these 2 points, which are 28,000 megaparsecs apart from one another, why should both of those points be at the same temperature? And we know that they're at the same temperature because we can actually, we've gotten information that's come back from these great distances, and as we say, everywhere we look in the universe, we're seeing the same thing. So it doesn't matter what 2 points we choose, but in any direction we look, we're getting energy back at the same temperature. I mean, that is so highly improbable as to be non-existent. So we have to. So that's the what has to be resolved there, and actually is the horizon problem part of this situation. And the other part is, why should the density of the universe be so very close to the critical density? And again, if you look at page 695, on the same page that I mentioned before, where figure 2711 is, and you look at figure 2710, you'll see that in the accelerating universe, for instance, you've got these 4 curves that I attempted to draw here and didn't draw very well to begin with, but you can see in your book, they diverge quite a bit once they get out to this time. But you'll notice that if we extrapolate back in time to t0, or very near t0, these points are very, very close to one another. So the idea is that the only way that there could be either no deviation or only a very, very slight deviation from critical density would be that the deviation there was very little, if any, deviation, but it actually grew rapidly in time, and that's what we see. If we actually bring everything back down to close to the Big Bang, this is indicating that it must have differed from the critical density in the past by only a very, very tiny amount. So that's what we see. That's what we see, and that also, as I say, has to do with the idea of the first thing was horizon. The second thing is what we call flatness. The other aspect of flatness is actually the physicality itself of flatness. If we actually think about if the universe actually had a finite curvature to begin with. Let's say at some point early on, the universe had some significant curvature to it. But it could deviate from flatness by no more today, could deviate in flatness by no more than 1 part in 10 to the 50th from the Big Bang through the inflationary period. Just as I said, because the Big Bang caused this inflation, caused it to expand by 10 to the 50th diameters so rapidly, it would only be 1 part in 10 to the 50th that we would actually see as a deviation. And your book goes on to give you as an illustration, you've got an ant who's walking on it wouldn't have to be an ant. I mean, we could be using something quite a bit larger than that. But to put this into perspective, they're taking some very tiny creature and putting that on a 10 centimeter balloon, a balloon that's inflated to 10 centimeters, about 4 inches in diameter, or I guess it's 4 inches in radius. So this is similar to that balloon that I showed you in the last lecture. You blow a balloon up, you put an ant on the surface of the balloon. The ant is aware of there being curvature on this balloon, because even something as small as an ant can see, as it's walking around, and after a certain period of time, the ant can actually walk all the way around the balloon and come back to where it started from. However, the same ant is not going to grow as the universe expands, just as I showed you last week that the galaxies didn't grow. The galaxies that I had attached to the balloon, they didn't grow, they just got further apart. When the universe expands, the ant is still the same size. Now the universe blows up, and now the ant is walking along this much larger sphere, the surface of a much larger sphere, which now has a radius of 10 to the 48th meters. The ant sees that, as you would well expect, as being completely flat. And that's what we're actually seeing. Now, quantum fluctuations, at a very small, at the quantum level, quantum fluctuations that occurred prior to expansion would actually become macroscopic during the inflationary period. So any little tiny minute fluctuation that was actually occurring now becomes very significant when the universe expands. And this would actually lead to us having regions of space with higher densities, and some of these regions would contain, let's say, perhaps a million or more solar masses. Now, these regions that had a million plus solar masses began to contract gravitationally post-inflation to million or million plus solar mass pre-galactic objects. But normal matter alone would not have been sufficient to cause the contraction that actually led to pre-galaxy formation. And this requires the idea of dark matter, as is pointed out in your book. Figure 2714 on page 699. But in the top figure, you see you've got a little diagram here showing you that around 1 second after creation took place, basically a universe that is dark matter dominated. Normal matter is a small part, and then dark matter is a much larger part. So this is the dark matter up here, and normal matter is down here. And this is 1 second after, and this is space expanding. And then after approximately a period of about 1,000 years, dark matter begins to clump together. And once that happens, so this is 1 second, but once that happens, we'll see where that initial line was up here, that we see something that sort of starts to look like this, which represents the clumpiness of the dark matter. And this is after, this is at about T 1,000 years. And then if we can take that all the way up to about 100 million years, what happens is this clumpiness becomes much more profound, and now we start to see something that looks like this. And the dark matter is contained in here. This is all dark matter, and under that, which is the normal matter, are these smaller areas, these much smaller regions down here. And this is where we see the galaxies and clusters and all forms of normal matter are contained in this little area, but the dark matter is still out here. So that's what's actually being illustrated there. And the other thing I wanted to say about it is it could be either hot or cold. Now, hot dark matter is lightweight particles, much less massive than an electron. And the only thing that we really have is that's less massive than an electron would be a neutrino. So the various kinds of neutrinos that we talked about would be the best candidates for hot dark matter. But small amounts of these would disperse and they wouldn't clump together to give our present day structure, a universal structure that we have. So we have to look to something called cold dark matter. And cold dark matter is, these are very massive particles, which does lead to a small scale structure. So the best model that we have is 4% normal matter for the universe, 23% what we now call cold dark matter, and 73% is the dark energy, and principally in the form of, or maybe entirely in the form of the cosmological constant. So that's astronomers' best guess, which I guess means that quintessence is not getting, probably is not getting any consideration then. If we actually look into, we've got a couple space shots, one of them called the COBE, that's the Cosmic Background Explorer, and another satellite, which is the Wilkinson Microwave and Isotropy probe, and that probe is abbreviated WMAP. So the COBE and the WMAP satellite observations, from both of these observations, the WMAP gives a finer structure than the COBE does, but they show very, very small deviations in the cosmic microwave background. And these deviations are on the order of 2 times 10 to the minus 4th kelvins. So that's 2 10,000th of a Kelvin. But this actually supports the dark matter concepts, since although it doesn't, dark matter doesn't interact directly with photons, radiation is actually influenced slightly by gravity, by the gravity of the dark matter that's present in the universe. These dark matter clumps, of which I alluded to prior to this, and this actually causes ripples that we can see in the microwave background. And what is actually calculated is the numbers that we're seeing. It's precisely what the COBE and the WMAP determinations are showing us is exactly what's predicted theoretically, if in fact all the things that I told you turn out to be true. And then we have something called the Grand Unified Theory superforce, after gravity actually decouples from the other forces. And this occurs at about 10 to the minus 43 seconds. Gravity decouples, and now we've got the 3 forces that are actually unified. And from approximately 10 to the 28th kelvins to about 10 to the 15th kelvins, I guess at 10 to the 28th, the strong force decouples from the gut superforce. And that leaves us, well, let's look at the forces that we actually have. So we start out with one unified force, but the individual forces that are comprised, that actually ultimately freeze out, we know that there are 4 fundamental forces. So let's look at these forces. So the strong force has a range of only 10 to the minus 15th meters. Particles getting further away from that, the force rapidly falls to 0. But what particles are subject to this force? Well, matter, anything made out of matter, protons, neutrons, etc. Anything in the nucleus is going to be subject to that force. So nuclear, we'll say nuclear matter. And it's mediated, the strong force is mediated, that is the particle that carries this. The mediator is the gluon. So this is the force, this is the distance that it actually is active over. This is what particles, what is subject to the force. Then we've got, after the strong force, we have the electromagnetic force. Electricity and magnetism, it's really one force. Distance, infinity, although it falls off rapidly with distance, but electromagnetic force doesn't have a range particularly. And what is subject to it? Any charged particle. And the electromagnetic mediator is the photon. Next thing is the weak force. Is the force, for instance, that is responsible for radioactive decay. Its range is about 10 to the minus 17th meters, even less than the strong forces range. What subject to this? Leptons, electrons, muons, tauons, neutrinos, things like that. And the mediator is the boson. We've seen the Z boson, W plus, W minus, and finally the graviton, gravity rather. Again, distance is infinite. Everything is subject to gravity. And the mediator is a proposed particle called the graviton, which no one has yet seen, but if our theories are correct, that's what we would expect to have, the graviton. So let's see. So I said that gravity decouples first, so we lose gravity. So that leaves us with a force that consists of weak, electromagnetic, and strong. The next thing to decouple is the strong force. So what we've got is the electroweak force. That's what we actually have. That's what it's referred to as the electroweak force. And the electroweak force, that's going to be good up until a temperature of 10 to the 15th kelvins, which would be a quadrillion degrees. And once the universe gets cooler than that, and all this is happening, remember, very, very rapidly. This actually happens at about 1/10 of a second after creation. The electroweak force decouples into electricity and electromagnetic force and the weak force. So that's all I want to say about this particular chapter.